Welcome back, students. In this video segment, we will look at section 11.2, series. Okay, in order to talk about series, I want to take us back to the beginning of section 11.1 when we talked about a made-up example of a sort of play involving three people, a waiter in a restaurant and two people on a date in that restaurant. And if you recall that the waiter, all the waiter did was to take the orders of the people on a date and write those orders in separate checks, and we called those separate checks sequences. In fact, all of section 11.1 had to do with sequences. Sequences are nothing more than lists of numbers, infinite lists of numbers, in a particular order. The numbers have to be in a particular order. And one of the people on the date ordered one pizza, then they ordered half a pizza, then a fourth of a pizza, then a half of that, 1/8 of a pizza, then a half of that order, 1/16 of a pizza, etc., etc., etc. And we said that this couple on a date, they were going to stay in that restaurant forever and continue to order pizza. And this is how the first person's check would look, what the first person's check would look like. And then we said that sequences, we have several ways of denoting them. We could also write, instead of the actual list itself, we could write what's called the general term for the sequence as a function. And instead of using the function notation like a of n, instead of doing that the way we normally do with functions, we put the independent variable in the subscript. So a sub n instead of a of n. And this gives us the general term of the sequence. And the general term looks like 1 over 2 to the n minus 1. Okay, where a sub 1 is 1 over 2 to the 1 minus 1, or 1 over 2 to the 0, which is 1. A sub 2 equals 1 over 2 to the 2 minus 1 equals 1/2, etc., etc., etc. Okay. So we also had another player in this sort of date game, pizza eating game. We had another player, and that second person on a date, ordered one pizza, then the second order was a half a pizza, just like the other person, but the third order was 1/3, and then the fourth order was 1/4, etc., etc. And we had a very different pattern to our second sequence. We could designate this sequence by stating its general term, by either using the same letter A or B or C. A sub n then would be 1 over n. If n was the first order, it would be 1 over 1 pizza. Second order, 1 over 2. Third order, 1 over 3, etc., etc., etc. Okay. The reason why we're here today is to talk about the point of view in that problem of the people on the actual date. And more specifically, remember, our point of view was in their stomachs. And when we do that, we have things called infinite series. We don't have to use the term infinite when describing infinite series. In fact, most often we just say series. A series is nothing more than the sum of the terms in a sequence. When you take all the numbers in the list and you add them up, you get what's called an infinite series, or just more plainly, a series. So the first person on the date, the series corresponding to what's in their stomach. First they consume a pizza, then they consume. So into that one pizza in their stomach, they add half a pizza. Then to that, they add a quarter of a pizza, 1/8 of a pizza, etc., etc., etc. Okay, this is an infinite series. An infinite series is an infinite sum of numbers. So series are never regarded as finite sums. Series are always regarded as infinite sums of numbers. And one way to designate them is to, just like the sequence, write out the terms in the series until we see a pattern. And then after the pattern, we write ... to indicate that the sum goes on forever. Another helpful thing is to write the general term occurring at some point in the summation, some finite place in the summation. And we do that by writing plus ... all the way up to, give me a second here, let me clean this up. There we go. 1 over 2 to the k minus 1. So we have 1 plus 1/2 plus 1/4 plus 1/8 all the way up to the general term at k at the kth order, or you could put the nth order, 1 over 2 to the n minus 1, and then plus ... after that. This is helpful for the reader, for the person who's looking at the series, to get the pattern right away without having to discover the pattern in the number of terms in the first four terms or 5 terms or however many terms we wrote as the person writing out the series. If we write the general term in there, there's no doubt as to what the pattern is. Okay. Well, in algebra we can't add an infinite number of terms. So what we do is we shorten our notation here by using the sigma notation for summation that we did with Riemann sums in Calc 1. So this is the capital Greek letter sigma, and you can think about it as abbreviating the words the sum of 1 over 2 to the n minus 1. So summing up the terms in the sequence as n ranges from 1 and stopping at k, that would give us the sum of the first k terms, and stopping there, and then taking the limit of that sum as k approaches infinity. And that covers every term in the sequence then. The limit as k approaches infinity allows us to consider an infinite sum or a series. So for the second person on the date, their series would look like 1 plus 1/2 plus 1/3. You could write out as many terms as you want in the beginning, plus ... all the way up to the general term, either with k or with n. Let's say up to the kth term would be plus 1 over k, and then we continue from there, plus ... and we write this as the limit as the number of terms becomes infinite, as we add more and more and more terms, of the sum of 1 over n ranging from 1 to that kth term. Okay, so again, we would be looking at adding up the first k terms, just as before, first k terms, and then taking the limit as the number of terms approaches infinity. Okay, well, we shorten the notation a bit, just like when we were considering how we're going to write the limit of a sequence. Remember, if we're considering the limit of a sequence, we could actually write the limit as n approaches infinity of 1 over, this is from 11.1, 1 over 2 to the n minus 1, and that equals 0. That means the sizes of the slices of pizza in the first person on the date are getting very small. Or we could simply write in a more easy fashion, or a more shorthand fashion, 1 over 2 to the n minus 1 approaches 0. We don't even have to write as n approaches infinity, because it's always assumed that n is approaching infinity. So that last thing I just said, it's always assumed that n is approaching infinity. The same thing goes true for series. There's no need to write the limit as k approaches infinity of the sum of the first k terms, so n ranges from 1 to k, 1 over 2 to the n minus 1. There's no need to write that. We can simply write the sum, n equals 1 to infinity of 1 over 2 to the n minus 1. Okay, and that's just fine. There's nothing wrong with that at all. In fact, that's the preferred way of completely writing out what the series looks like. So generally, what does a series look like? It's a sum. Series are infinite sums. Sequences are infinite lists, no adding up of the individual terms in the sequence. A series you get by adding up all the terms in the sequence. Okay, so that in general, the sum of a sub n as n ranges from 1, and by the way, n doesn't have to start at 1, but we'll follow our author's lead, and very often we have in this course n starting at 1 or 0, but n can start at 5 or 15 or 500,000. This equals the limit as k approaches infinity of the sum of the first k terms of the series. That sum of the first k terms, by the way, let me write that out. That sum of the first k terms, if we ditch the sigma notation, this is a1 plus a2 plus ... all the way up to a sub k. The sum of the first finite number of terms in a series is called a partial sum. A partial sum. Let me illustrate that here. This in red is called a partial sum. And that kind of makes sense to use the term partial sum. Partial sum as opposed to the total sum, or the value of the limit as n approaches infinity. So a partial sum of a series is obtained by adding any number of terms in the series together. Okay. So remember back in our example, or from our first example, we had that one of the people on the date was going to live, and I never proved it. We'll actually look at the proof today. That we said that one of the people lived. In fact, the first person lives. The first person whose orders obey the pattern. Each subsequent order, the next order is always 1/2 of the previous order. That person ends up living, meaning that through all time, up until the end of time, the amount of pizza in their stomach will not blow up. They won't be eating an infinite amount of pizza. In fact, I think I let the cat out of the bag and said that series actually equals 2, whereas the other person, unfortunately, would die because their stomach would eventually have an infinite amount of pizza in it. But I also said that particular series, the one where we had 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc., that series approaches infinity, but very, very slowly. So the first person with whose series actually equaled a finite number, that series is said to converge. So the sum 1 over 2 to the n minus 1 as n ranges from 1 to infinity, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, etc., etc. This series converges. And we'll look at a proof of that very soon. Converges, and actually converges to 2, which, if you kind of think about it, is kind of bizarre. If you really think about it, what did their series look like? It looked like one whole pizza plus 1/2 a pizza plus a fourth of a pizza plus an eighth of a pizza, most of the pizza that they ate was in the first two orders. Or even if you look at the first three orders. In the first three orders, 1 plus 1/2 plus 1/4, that's 1 3/4. Most of the pizza that they end up eating is in the first three orders. The other 1/8 plus all the way out to infinity, that just equals a quarter. That equals a quarter. Okay, it's kind of bizarre that an infinite sum could be such that the most of the sum occurs in the first few terms. Okay, all right. So let's dig into the idea of convergence. Well, with the idea of convergence comes the opposite of that, divergence. The sum of the orders of pizza throughout all time in the second person, that person ends up eating an infinite amount of pizza. So this series diverges. To diverge, a series need not approach infinity. The sum need not approach infinity. To diverge simply means to not converge, to not converge. Convergence means the sum approaches a constant number, a finite number. To diverge simply means the series doesn't approach a finite number. And one way for partial sums to not approach a positive number is to approach infinity, but it's not the only way. So here's a quick example in green. The series 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc., etc. This series does not converge. If you add the first two terms, if you have the first term only, you have 1. If you add the next term, you get 0. If you add another term, you get 1. If you add another term, that is subtract 1, you get 0. So half the time, this partial sums equal 1. Half the time, partial sums equal 0. So this series does not approach a single number, so it diverges. It's not a real pleasant example when you think about it pizza-wise. It's saying that, let's see, how can we say this and not be too gross? It's saying that the person eats a pizza, then digests the pizza. So ultimately, when they're done digesting the pizza, they have no pizza in their stomach. Then they order another pizza. Well, then they have a pizza in their stomach. Then they digest the pizza. So as time goes on, it depends on when you catch this person as to how much pizza they'll have in their stomach. At any point in time, they'll either have one pizza in their stomach or they will have nothing in their stomach. So there's not one number to which this sum converges, so the series diverges. Very often, the series divergence gets us that the series is approaching infinity, but it's not necessary. It's not always the case. Okay, so let's take a look at a very special series. In fact, we already looked at two of the most important series for the whole remainder of the course. That the series that are representing our people on the date, those are extremely important series for us. So let's take a look at one of them. Let's assume that I didn't let the cat out of the bag about the series in that example. So determine whether the series, the sum 1 over 2 to the n minus 1, n ranges from 1 to infinity, converges or diverges. Converges or diverges. There we go. Or diverges. Okay, so here's the plan. I'm going to use a very special trick to answer the question about this, or to solve the problem about regarding this series. This trick is not a trick that you're going to use in practice. The trick, though, does get you used to thinking about series. and that's a real important thing. A very important aspect of the rest of the course, and I think I mentioned this, and an aspect that makes this some of the hardest material for the whole course is we have to start visualizing numbers. We have to sort of develop an intuition for patterns of numbers, and this is showing. Determining whether the series converges with this trick, yeah, it's good practice. So let's do it. Let's let S as in Sam sub k represent a partial sum in this series. Let's say it represents the sum of the first k terms in this sequence. So S sub k equals the sum of the first k terms in this sequence, a series. I'm making a mistake. I've made a mistake a couple times. It's very common, and it's interchanging the words series and sequence. So let's say the S sub k is the sum of the first k terms in the series. So what does that mean? It means that S sub k is the sum of the terms in the series 1 over 2 to the n minus 1 as n ranges from 1 to k. So let's write that out. When n equals 1, I get 1. When n equals 2, I'm adding 1/2. When n equals 3, and I'm going to write the third term, but I'm not going to write it as 1/4. I'm going to write it with its exponent still intact. So this is 1 over 2 squared. When n equals 4, I have 1 over 2 cubed plus ... Remember, this is not the whole series. This is just the sum of the first k terms. So this is plus 1 over 2 to the k minus 1. Okay, so here's the trick. I'm going to take this equation and I'm going to multiply both sides by 1/2. I'm going to multiply both sides by 1/2. So I'm going to multiply the left-hand side by 1/2. I'm going to multiply the right-hand side by 1/2. Well, if I multiply 1 by 1/2, I get 1/2. And I'm going to move that, I'm going to scoot it over a little bit. I'm going to multiply 1 by 1/2, but then I'm going to move it so that it's directly beneath the 1/2, the next term in the sequence above. And I'm going to continue doing this. I'm going to take the second term and multiply by 1/2. If I multiply 1/2 times 1/2, I get 1 over 2 squared. But again, I'm going to scoot it over so that it's right beneath the 1 over 2 squared in the original partial sum. I'm going to keep doing this. So this is 1 over 2 cubed plus ... If I multiply 1 over 2 to the k minus 1 times 1/2, I'm going to get plus 1 over 2 to the k. Okay, so what would the term just before 1 over 2 to the k in that second line be? Well, what would the term in the first line be just before that? In the line just before, we would have 1 over 2 to the k minus 2. Remember, if we start at the end and go backwards, the exponents are decreasing. So it would be 1 over 2 to the k minus 2. If I multiplied that by 1/2, I'm going to get 1 over 2 to the k minus 1. So I just slipped another term in there just to see what would be right beneath 1 over 2 to the k minus 1. Okay, now here's more of the trick. I'm going to take both sides of the equation and I'm going to subtract. So I'm going to take s sub k minus 1/2 s sub k, and I'm going to take the first line and subtract the second line. If I do that, on the left-hand side, it's real simple. I have 1 s sub k, and I take away 1/2 s sub k. That leaves me with 1/2 s sub k. Okay, that's on the left side. Remember, s sub k is the sum of the first k terms. Now look what happens if I start subtracting on the right-hand side. If I subtract starting with 1, I have 1. And notice I have 1/2 minus 1/2, that's 0. Then 1 over 2 squared minus 1 over 2 squared, that's 0. 1 over 2 cubed minus 1 over 2 cubed, that's 0. All the way up to 1 over 2 to the k minus 1 minus 1 over 2 to the k minus 1, that's 0. And the only thing left that doesn't cancel out is minus 1 over 2 to the k. This is very rare in series that we can do this sort of thing, to collapse the sum of the first k terms into just a couple of terms. If you don't get what I just said, let's look at this written a little more compactly. It says that 1/2 of the sum of the first k terms is 1 minus 1 over 2 to the k. If I multiply both sides by 2, I get the sum of the first k terms is 2 times 1 minus 1 over 2 to the k. Keep in mind, again, that this s sub k, that is the sum of the first k terms in this series. It's the sum of 1 over 2n minus 1 as n ranges from 1 to k. That's equal to 2 times 1 minus 1 over 2 to the k. So what's the value of the series? Well, how do we get the value of a series? We take the limit of the partial sum as n goes to infinity. We imagine taking the limit of both sides of this as k goes to infinity. Limit as k goes to infinity. Limit as k goes to infinity. Well, left-hand side, as k goes to infinity, you get the whole series. The sum 1 over 2 to the n minus 1, n ranges from 1 to infinity. Right-hand side, as k goes to infinity, the only thing that we really need to concentrate on is the 1 over 2 to the k. As k gets big, 2 to the k gets huge. This term goes to 0. 2. The sum of this series is, in fact, 2. This proves that the first of the two people on the date is going to live. As long as their stomach can hold 2 pizzas, they're going to live. To show that the other person dies, I think a little less harshly would be to say to show that their series diverges takes a little bit different of a trick. So we'll handle that time-wise, I think about 15-20 minutes or so from now. Okay, I want to concentrate on this first series that we just looked at. This series is arguably an example of the most important series for the whole semester. And I'm not exaggerating here. This is an example of, I believe, to be the most important type of series in this in this course. This series is an example of a geometric series. The most important, of course, my opinion, series in the whole course. Okay, so what are the features of a geometric series? What makes a geometric series? Well, you've seen one. A geometric series behaves like this. Starts out with a constant. Then the next term is a fraction of that constant. The next term is that constant times some fraction. And that's exactly how the first person on the date did their second order. They ordered 1/2 of their first order. The next term is that same constant multiple of the previous term. So the next term is 1 times 1/2 again. So 1 times 1/2 squared plus 1 times 1/2 cubed. This is the type of pattern that a geometric series follows. One, the nth term, if you will, the nth term is 1 times 1 over 2, 1/2, to the n minus 1. And it's n minus 1 instead of n. Notice when n was 2, the exponent was 2 minus 1. When n is 3, the exponent is 3 minus 1. Okay, so the fact that it's 1/2 to the n minus 1 is kind of an important thing in our general form that we're looking for. Okay, so what does a general geometric series look like? So generally, a geometric series is any series that can be written in the form a constant plus a constant times a number plus a constant times that same number squared plus a constant times that same number cubed plus somewhere in the series a constant times that number to the n minus 1 and then off to infinity, or the sum of a r to the n minus 1 as n ranges from 1 to infinity. This is something that you're going to want to remember. This is the most important series in our course, and the reason why that's true is going to become apparent to you as we get through these sections. So I'm highlighting the geometric series. I'm trying to highlight the geometric series in a different color. There it is. So that you identify real early on what that general form looks like. So a geometric series is any series of the form the sum of ar to the n minus 1, n ranges from 1 to infinity. Okay. Well, what affects the convergence or divergence of this series? Well, think about this series as being the most general case of the kind of orders that the first person on a date could do. That a in the first term of the series, that's their first order. In our example, it was 1 pizza. The r was the fraction of their previous order that they ordered for their next, and it was 1/2, for example. The first on a date ordered 1 pizza, a equals 1. Then for their subsequent orders, each subsequent order was 1/2 of the previous one, so r was 1/2. So this is the general case where the person orders a pizzas to begin with. They could be 1, they could be 5, they could be 100 pizzas. And r is the fraction, if you will, of the previous order that they order for their next order. R doesn't have to be a proper fraction. For our case, r was 1/2. It could be that the person orders 5 pizzas, a equals 5, and then their subsequent orders are 1.5 times their previous order. So for each order, next order, they order 150% of their previous order. That's 1.5, or r equals 3/2. clearly, intuitively, if a person does that, if a person orders 5 pizzas and their next order is 5 times 3 halves, and their next order is the previous order times another 3 halves, that their orders are getting bigger and bigger and bigger, and as they eat throughout time, their stomachs are going to explode. So that series couldn't possibly converge. What does that leave for the series? Well, if it couldn't possibly converge, that means it diverges. Okay. In fact, I think what we'll do is once we determine what it takes for a geometric series to converge, we'll look at that example, that next example. Suppose someone comes in, orders 5 pizzas, and that their next orders, their subsequent orders are 150%, that is 3 halves of their previous order. Let's see what happens with the numbers with that. We already have an idea that that person should get, their stomach should explode very quickly. Well, we'll prove it. Okay, so let's handle this generally. A geometric series. I want to know what affects convergence or divergence. Is it the first order of pizza? Strangely, it's not. A has very little effect. The first term, A, the first order, if you will, of pizza has very little effect on the convergence or divergence of the series. Clearly, if A is 0, if a person doesn't order anything, then the series converges to 0. It doesn't matter what fraction of 0 you order for your next order, you're still ordering nothing. But other than that, A has absolutely no effect on the convergence, the first order of pizza, or the first term in the geometric series has no effect, other than when A equals 0, on the convergence or divergence series. Well, what does that have? What's left? And it makes sense. What's left should be the thing that determines whether this series diverges or converges. It's the percentage of your previous order that you multiply that previous order by to get your next order. That is what determines whether you're going to have a series that converges, a stomach that's going to remain finite in size, or diverges, a stomach that explodes. Let's prove that. Let's not only prove that, let's determine exactly what percentage of your previous order, if you will, you could order for your next orders and add infinitum and still have convergence. Okay, let's do this. We'll stop talking about it. All right, so a geometric series. A geometric series, remember, is any series of the form sum a r to the n minus 1 and ranges from 1 to infinity. Or, let's do what we did in the last example. The sum of the first k terms is first order of pizza plus fraction of the first order of pizza, a times that fraction. Next order is that same fraction times the previous order. A times AR is AR squared plus ... all the way up to AR to the K minus 1. That's the sum of the first K terms, the sum of the first K orders of pizza, if you will, or the sum of the first K terms in a geometric series. I'm going to multiply both sides by R. I'm using the same trick I did with the original series. I multiplied both sides by 1/2 before. It's no longer 1/2. The percentage, or the R value, is now some number that's not specified for sure. So if I multiply the left-hand side, I get R S sub k. If I multiply the right-hand side, the first term, A times R, is AR. And I'll write that right below the AR above. The next term is AR times AR, AR squared, plus ... all the way up to AR to the K. The term just before AR to the K should be AR to the K minus 1. Then I'm going to do exactly again what I did before in the previous example. I'm going to subtract second line from first line. And if you weren't sure where those numbers came from, I multiply a times r, then ar times r, then ar to the k minus 1 times r, etc., etc. Okay, so let's see what happens. Well, what is the left-hand side? It's s sub k minus r times s sub k. The right-hand side, almost everything cancels out. I have a, and then ar minus ar cancels. Ar squared minus ar squared cancels, all the way up to ar to the k minus 1 minus ar to the k minus 1. Cancel, 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 all the way up to minus ar to the k. Left-hand side, factor out the s sub k. 1 minus r. Right-hand side, factor out the a. Little bit of algebra. Divide both sides by 1 minus r. So that gives us the sum of the first k terms, the first k orders of pizza, collapse into a times 1 minus r to the k over 1 minus r. Okay, so what we need, we don't need the sum of the first k orders of pizza. We need the sum of all the pizza. Okay, so let's do that. That means we need to take the limit of both sides as k goes to infinity. All right, so keep in mind that the sum of the first k terms is the sum of the ar to the n minus 1 as n ranges from the first order to the kth order, and then the limit of that as k goes to infinity, or the limit as k goes to infinity of the right-hand side, a1 minus r to the k over 1 minus r. That limit on the right-hand side might look real complicated. It's not at all very complicated, that limit. K is approaching infinity, so everything else in that limit on the right-hand side is constant. So just to emphasize that, I can factor the a over 1 minus r out of that limit process. If I do, I have a over 1 minus r. Remember, you can factor constant multiples outside of limits, times 1 minus r to the k. And in that remaining limit, the only thing that's going to affect the value of the limit is the limit of the limit of r to the k. Look, the only thing that's going to affect the value of this limit is the limit of r to the k. So let's look at that. Let's take a look at what this all boils down to. This all boils down to what happens with the limit as k goes to infinity of r to the k. Now remember, that r, that's the fraction of your previous order that you order for your next order. First example, the person was ordering a half of their previous order each time because they were filling up and they only needed a half of the previous order to get their next order. So if r was 1/2, you'd have 1/2 to the k. If r was 1/2, you'd have 1/2 to the k. If r was 1/2, you're looking at 1/2 to the k. What does that equal? It equals 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. How many factors of a half? K. K factors. What happens when you take a half and multiply by a half? You get something smaller. Multiply that by a half, you get something even smaller. If you keep taking a half and multiplying by a half, you get a sequence of numbers that are getting very, very, very small. Half of a half is a fourth. 1/2 of that is 1/8. 1/2 of that is etc., etc., 1/16. So that approaches 0. So for what else does that r to the k approach 0? How about 2/3? 2/3 of 2/3. 2/3 times 2/3. R is 2/3. 2/3 times 2/3 is smaller than 2/3. 2/3 of something is smaller than the thing you started out with. If you keep multiplying something by 2/3, you keep getting something smaller and smaller and smaller and smaller. 2/3 is about 67%. If you take 67% of something, you get something smaller than you had. If you take 67% of that, that becomes smaller, etc., etc., etc. It seems like then, if r is any fraction less than 1, that r to the k should approach 0. Well, what about if we keep going less than 1? Like what if r equals -1/2? What then will -1/2 to the k look like? Well, -1/2 to the k will look like -1 to the k times 1/2 to the k. And I want you to try to remember what happens, what that -1 to the k does to a sequence. That -1 to the k, all it does is it makes the term in the sequence oscillate between positive and negative. So when that k value equals 1, when k equals 1, you get -1/2. You get -1/2. When k equals 2, you get +1/4. When k equals 3, you get +1/8, -1/8. So the numbers are getting very, very small, but they're oscillating between plus and minus. What that means is, remember our examples earlier, it means that the numbers -1/2 to the k form a convergent sequence, and they're getting very close to 0, but they're bouncing back and forth across 0 on the number line. Hard to draw -1/8 on the number line. So back and forth and back and forth, back and forth, back and forth. The upshot of this is that if r is a negative fraction, proper fraction, then r to the k will approach 0. What this is telling us, just to sort of cut to the chase, is that the limit of r to the k as k approaches infinity is 0 if r is some proper fraction between -1 and 1. Okay? If that's true, so if r is between -1 and 1, that is, if the absolute value of r is less than 1, then look back at our series. The sum, n goes from 1 to infinity, ar to the n-1. Remember, we're looking at the limit on the right-hand side, is a over 1 minus r times the limit as k goes to infinity of 1 minus r to the k, but r to the k approaches 0 if r is between -1 and 1. So the series then converges to a over 1 minus r. This is extremely important. So if r, that fraction of the previous order that you order for your next order in terms of interpreting geometric series as the generalized pizza example, if r is between -1 and 1, the series will converge. Not only will it converge, we know what it converges to. It'll converge to a, your first order, over 1 minus r. Okay? Let's see if our first example works. Back to our first example. Back to first example. Our first example was the sum, just the first date on the first of the two people on a date. 1 over 2 to the n-1 and goes from 1 to infinity. That's their sum. Can be written in the form 1 times 1/2 to the n minus 1. A is 1. R is 1/2. The absolute value of R is 1/2, which is less than 1. That's what we needed for converges. So the series converges to A, the first order of pizza, over 1 minus R. 1 minus 1/2 is 1/2. 1 over 1/2 is 2. So this example, or rather this conclusion that we make, if R is between -1 and 1, that the series converges to A over 1 minus R, it works in the first example. It must. It must. Okay, so let's finish this off. So we know that the geometric series converges if the absolute value of R is less than 1. What if the absolute value of R is not less than 1? What if, let me go back to my black pen here, the absolute value of R is not less than 1. Suppose, what if the absolute value of R, let's do it this way. Let's say, what if R is 1? Okay, in our geometric series. Don't lose the example that we're using to do this. We're thinking about the geometric series as the generalized pizza problem. Order a pizza. What's the order size? A. What's the fraction of your previous order you want to get to your next order? R. Well, if R is 1, what does that mean? 1 is 100%. 1 equals 100%. That means for your next order, you're going to order 100% of what you ordered before. So if R equals 1, remember the geometric series is A plus AR plus AR squared plus forever and up on and on forever. S equals A pizzas, even if A is 1, plus A times 1. A times 1 is A. Your second order is the same thing as your first order. Your third order is A times 1 squared. Plus dot, dot, dot. What's going to happen? Unless A is 0, you're going to explode. You have A, now you have 2A, then 3A, then 4A. Even if A is 1, if you have a pizza, you add another pizza, you have 2 pizzas. You add another pizza, you have 3 pizzas, 4 pizzas, 5 pizzas. So the series diverges if A is more than 1. I hope it's clear that the series diverges if R is more than 1. If R is more than 1. What if R is more than 1? If R was equal to 1, the series diverged. What if R is more than 1? What if R equals 2? Sum of the pizzas in your stomach. A pizza, say A equals 1. Then 2 pizzas plus 2 squared times A plus A times 2 squared plus A times 2 cubed plus dot, dot, dot. A plus 2A plus 4A plus 8A plus, what's going to happen? Even if A is 1 pizza plus 2 pizzas plus 4 pizzas plus 8 pizzas, you're going to explode. The series diverges. We don't have to look at this as a pizza problem. Go back to the sum with me, if you will, the sum of the first k terms and then the limit of that. The sum of the first k terms is, the sum of the first k terms, so up to k, starting at 1, AR to the n minus 1, that was A over 1 minus R times 1 minus R to the k. And then we took the limit of both sides as k goes to infinity. We order K pizzas, or K orders, not K pizzas, we make K orders, and then we let the number of orders approach infinity. And remember that limit only depended on what happens with R to the K. So if R is something more than 1, like 2 to the K, or 3 to the K, or 4 to the K, or 7 halves to the K, what happens with 7 halves to the K? 7 halves is 3.5. 3.5 times 3.5 times 3.5 times 3.5. 3.5 is 350%. What happens when you take 350% of something, then 350% of that, you get bigger and bigger and bigger and bigger. That limit then should be infinity of R to the K if the absolute value of R is greater than, not if the absolute value, just R. If R is greater than 1. Okay. We can make a similar argument for the rest of the possible values for R. And we'll do that real quickly. What if R equals 1? What if R, equals -1? Well, if R equals -1, then your sum looks like A plus AR plus AR squared, -1 squared is 1, minus AR cubed, etc., 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 etc. You have A pizzas. Then you remove A pizzas, that's 0. Then you add A pizzas, there's A pizzas again. Then you remove A pizzas, is 0. Divergent. Doesn't approach infinity. Through all infinity, half the time you're observed you have A pizzas in your stomach, and half the time you have nothing in your stomach. The same argument can be made if R is less than -1. So the bottom line, and this is a huge bottom line if you got lost in all this computation, that the geometric series, this is again, I think I said it a couple times, this is the bottom line about geometric series, and you memorize this is very important for you, is the sum of AR to the n-1 as n ranges from 1 to infinity does one of two things. It converges to A over 1 minus R if the absolute value of R is less than 1, and diverges otherwise. Diverges if the absolute value of R is greater than 1. Okay? So let's go back to that example I kind of pulled out of thin air. Let's see if I can remember my example. I can't quite remember, but I think the example was first order. So first pizza, order 5 pizzas. You could always pause the tape and go back. I don't think that's necessary though. First order of pizzas, 5 pizzas. And suppose that each subsequent order, this is where I can't remember, each subsequent order is, let's say, 1.5 times the previous order, 150% of what was ordered before. This series is geometric. The series that represents the pizza in this person's stomach is 5 pizzas plus 5 times 3 halves plus 5 times 3 halves times 3 halves, or 5 times 3 halves squared, plus 5 times 3 halves cubed, etc., 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 forever and ever and ever and ever. This is geometric. It's geometric with A equal to 5 and R equal to 3 halves. The important thing for us is that the absolute value of R is 3 halves, which is greater than 1. So the series diverges. Okay. So how about a counterintuitive example, something that may not make sense in terms of convergence or divergence? What if the first pizza order was a humble one pizza, just like in the very first example in the last video segment, one pizza ordered, but the subsequent orders, they didn't quite order a whole pizza again, or the whole order, the previous order, but they ordered 99% of their previous order. So you order a pizza. Picture this. You order a pizza. Then your next order, you tell the waiter, I want 99% of what I just ordered. They're going to give you very close to another pizza. It's going to be hard for them to remove 1% of pizza. They might take an anchovy off. If you don't like anchovies, they might take an olive off. Okay, or a piece of pepperoni. Now I'm getting hungry. But your next order is going to be pretty close to the previous order. So are you going to, if you keep doing this forever, are you going to live or die? You're going to live. Live meaning the series is geometric. The series looks like one pizza plus the whole pizza, but 99% of that. Next order is previous order, 1 times 0.99, but 99% of that. So multiply by another 99, et cetera, et cetera, et cetera. This is geometric. This is geometric with A equals 1 pizza and R equals 99% or 0.99. The absolute value of R is 0.99. 0.99 is still less than 1. So the series converges. This person can really be a pig, pardon my language. They can just keep ordering 99% of what they ordered before. How much pizza in stomach at the end of time? So how much pizza consumed after end of time? Well, the sum of A, 1 pizza, R, 0.99, to the n minus 1, n ranges from 1 to infinity, is A over 1 minus R. A over 1 minus R. Well, what's 1 minus 0.99? It's 0.01. It's 1 over 100. This is 1 over 1 over 100. So the person's going to have a big tummy. Person's going to have 100 pizzas in their stomach at the end of all time. But it's still a far cry from an infinite amount of pizza. Okay? Bottom line. The bottom line is above. Our bottom line above, I want to highlight this. If my surface will allow me to do this, I want to highlight this in red. Okay? In red, the most important series is the most important series for our whole semester. We're going to be talking about a lot of series in our next few weeks, lots and lots of them. But this is the most important one, and you're going to see why very soon. And it has very little to do with ordering pizza, although it sounds pretty good. Okay. I'm going to take a small break. I would suggest that you do stretch your legs, maybe, or you can just hang on for a couple seconds, and we'll pick up with another example. Okay, let's take a look at another example. Let's take a look at the example. The directions are to determine whether the following series converge or diverge. Determine the value of the convergent series. For most of our work, up until maybe the last week or week and a half of our semester, we're going to be interested in the first part of this problem. We're going to be interested in simply determining whether a series converges or diverges And secondarily, will be what will be of secondary concern will be the value of the convergence series, and then that second thing will become more and more important as we move on. So for now, mostly we're going to be interested in the convergence or divergence of a series. To what the series converges is not quite the most important thing. Okay, but let's do that. Let's do both for this particular example. So our first example starts out with the sum of 4 times 2/3 to the n minus 1, as n ranges from 1 to infinity. We recognize that this is a geometric series. It is exactly of the form a r to the n minus 1, where n ranges between 1 and infinity. And since that's the case, we identify this series. The series is geometric with the absolute value of r equaling 2/3, which is less than 1. So the series converges. That was the condition that needed to be met for convergence, and it converges to a is the first term, 4 over 1 minus r, 1 minus 2/3. 1 minus 2/3 is 1/3, and 4 over 1/3 is 4 times 3, or 12. So this series converges, the most important thing, and it happens to converge to 12. Suppose we take a look at another example. The series starts out with a 4, but r is 3/2 instead of 2/3. R is 3/2. This series is exactly in the form, again, of the sum of ar to the n minus 1. N ranges from 1 to infinity, so it is geometric. So it's geometric with the absolute value of r equals 3/2, and it's more than 1. So the series diverges. The series does not converge. The series diverges. Once we determine we have a divergent series, there's nothing else to do with it. The series does not converge. The sum does not approach a finite number. Okay? All right. By the way, a little bit of a note in terms of what I expect you as a student to write on homework, and just as importantly on an exam, is when you're asked to determine whether a series converges or diverges, I would like you to state all reasons for your conclusions. So specifically here, in parts A and B, I started with a statement that the series was geometric, okay, and then named the actual condition that was met for convergence, or not met in the second case of part B. So I want you to state everything when you're asked to determine why a series converges or diverges. The value of the convergence series was given here because that was part of this problem. But if we were only interested in convergence or divergence, we wouldn't have stated the value in part A of the convergence series. Okay, so C. Suppose we look at a series, or we're looking at a series that looks like this. K goes from, let's say, I'm using n. The variable in the series is not important, but I'm going to try to stick with what our author uses mostly. Suppose we have a series that says n equals 2 to infinity of 1/5 to the n plus 4. This series is not exactly in the form ar to the n minus 1. N goes from 1 to infinity. But it is geometric. There are a couple ways of recognizing this. The first, a very revealing way to recognize this would be to write the series out, write the terms out, write the first few terms out. When n equals 2, I'm looking at 1/5 to the 6th power. 1/5 to the 6th power, whatever that number might be, equal to if we were to multiply 1/5 to the 6th out. The next term, when n equals 3, I have 1/5 to the 7th power, then plus 1/5 to the 8th power, plus ... So this is 1/5 to the 6th. The next term is 1/5 to the 6th times 1/5. That gives you 1/5 to the 7th. The next term is 1/5 to the 6th times 1/5 squared. If you add the exponents up, you get 8. So this is exactly in the form a plus a r plus a r squared plus ar cubed plus ar to the 4th. This is exactly in the form necessary to identify a geometric series. If you're still not there, I think you're probably going to be able to see that. But you could also write this in sigma notation as a r to the n minus 1. N ranges from 1 to infinity. This series can be written, if you write it out, you can see that it's geometric in form, or you can rearrange each term to get a new sigma notation, and goes from 1 to infinity, and identify it as a r to the n minus, the sum of a r to the n minus 1. I identify it directly as the sum a r to the n minus 1, where n ranges from 1, where it's supposed to start in our general theory, and go to infinity. Okay, so this series is geometric. So we would state at this point that the series is geometric with r, the absolute value of r, equal to 1/5, and that's less than 1. So the series, converges. And we were also asked to figure out to what the series converges, so it converges to a 1/5 to the 6th over 1 minus 1/5. 1 minus 1/5 is 5/5 minus 1/5, or 4/5. So this is 1/5 to the 6th over 4/5, or 5/4 times 1/5 to the 6th, or, my goodness, 1/4 times 1/5 to the 5th, and I wouldn't expect you to multiply that out. So that's the value for us for now. So the bottom line, this third example, sometimes series don't appear to be geometric initially in the sigma notation, but they turn out to be. So how do you recognize it? Well, write out the terms in the series. Write out the terms in a series and see if you can do what I did at the second line here. See if you can do what I did at the second line here. See if you can make the series into a constant plus the same constant times r plus the same constant times r squared, etc., etc., etc. There is a kind of a hint I can give you. Geometric series, or rather, a series will be a geometric if it looks like n starts from anywhere to infinity of a r to the n plus or minus I want to be careful how I summarize this. N plus any positive whole number, whole number. So n equals 50 to infinity of 13 times 2/3 to the n plus 17. That is a geometric series. We could do exactly what we did with the part C example and force this to be exactly of the form ar to the n minus 1, the sum, ar to the n minus 1, and ranging from 1 to infinity. We could do it. Not only that, we can identify r, the absolute value of r, to be 2/3, which is less than 1. Series converges. Therefore, series converges. Okay. There's a little bit of a hint for dealing with series that don't exactly fit the mold. All right, we're almost done with the section. There's a part of the section in the textbook that I would like you to read on your own, and it has to do with something called telescoping series. It's not difficult reading, but I'd like you to read about telescoping series. In section 11.2. They play a small role in our course. I don't want to occupy video time with this small part of the course. I want to stick to what's mostly important here. I think there are 2 or 3 homework problems regarding telescoping series. And again, it's easy reading. If you have any problems, just shoot me an email, and I'll get back to you guys on that. Okay. I want to return to the original example: the 2 people on a date. The second person on the date who did not live, the person who ends up eating an infinite amount of series. What did their series look like? Their series looked like the sum 1 over n ranges from 1 to infinity. This is also an extremely important series for our course. Extremely important series for our course. It diverges. There are several ways of showing that this diverges, several easier ways than I'm going to show you now to show that this series diverges. In fact, this is a good time for me to plug what's coming up in our next sections. In our next sections, you're going to be learning several tests for series to determine whether they converge or diverge. And ultimately, a lot of the problems you'll be encountering will play out like this: that you'll be asked to determine whether a particular series converges or diverges, and you try to identify the series as being of a certain type, and then you look at the theory regarding that type. So specifically, if we look back at a few minutes ago, that example that we just looked at, part A, determine whether that series converges. You will encounter a series of that sort, and you will recognize that it's geometric, and then you will apply the theory regarding geometric series. That is, you identified the absolute value of r, and it's less than 1, so the series must converge. While geometric series are extremely important, they're only one example of many types of series. So you'll learn more techniques for determining convergence or divergence. And in fact, before the end of this section, we'll look at a test for divergence. It's very important. Okay, so back to the series that occurs in our first example in 11.1. with the second date who is eating pizza, orders one pizza, then eats a half a pizza, then eats a third of a pizza, then a fourth of a pizza, then a fifth of a pizza, etc., etc., etc. Just like the other person on the date, the orders of the pizza, the individual slices of pizza that they're ordering are getting small. They're approaching zero. The person orders an entire pizza, then orders a half a pizza, then a third of a pizza. I can't draw one third of a pizza. A third of a pizza, then a fourth of a pizza. This is supposed to be drawings of the different orders. Then a fifth of the pizza, then a sixth of the pizza. The slices of pizza, sorry about that, my drawings of slices of pizza aren't very good. But they kind of make the point that the orders are getting small. The individual pieces of pizza are approaching zero in size. And that's not enough for convergence. It's not enough that the individual numbers that you're adding together in a series are getting tiny. It has to do with the way they're getting tiny. More about that coming up. I want to show that this series diverges, even though the individual slices of pizza are getting tiny. So let's do it. Let's take a look again at this sum, but I'm going to write a little smaller because I'm going to need quite a few more terms to look at. So the series looks like 1 plus 1/2 plus 1/3 plus 1/4 plus, I'm going to write out quite a few more terms. Not that many, but a few more. So 1/6, 1/7, 1/8 plus, and this goes on. And I'm going to regroup some of these terms together. I want to group 1/3 and 1/4 together. I want to group 1/5 through 1/8 together. In the next part of this series, I want to group together 1/9 plus ... all the way up to 1/16 together. Let's see this. 1/16 together. Bear with me for a second. Hang on a second here. Oh, here we go. 1/16. And then, of course, this goes on forever and ever. Okay. Now, I'm going to replace some of the numbers with smaller numbers. So here's what I mean. This series equals 1 plus 1/2 and 1/3. 1/3 is greater than 1/4. So I'm going to replace 1/3 with 1/4. I'm going to replace 1/3 with 1/4. So I have 1/4 plus 1/4. I can't do that without changing the value of the series. So see that equal sign? It gets replaced with greater than. I've replaced 1/3 with something that's smaller than it. So 1/3 plus 1/4 is greater than 1/4 plus 1/4. I'm going to replace 1/5 plus 1/6 plus 1/7 with 1/8. So plus 1/8 plus 1/8 plus 1/8 plus 1/8. 1/5 is more than 1/8. 1/6 is more than 1/8. 1/7 is more than 1/8. So I'm making the original series more than this new series I'm creating. Okay. And I want to show that this new series diverges. Why? I want to show that this new series diverges. Well, my series is more than this new series. So if my series, the sum of 1 over n, is more than this series that I'm creating that supposedly diverges, then it must diverge also. If you didn't catch that logic, stay tuned here. I'm going to replace 1/9, 1/10, 1/11, 1/12, 1/13, 1/14, and 1/15 with 1/16. I'm replacing 1/9, 1/10, 1/11, 1/12, 1/13, 1/14, and 1/15 with 1/16. So my original series that has those 1/9, 1/10, 1/10 is more than the series I get by replacing all those lesser numbers between 1/9, or those numbers between 1/9 and 1/15 with 1/16. I'm going to keep doing that forever. Well, what do I get? I get that my original series then is more than 1 plus 1/2, 1/4 plus 1/4. What is it? It's 2/4. It's 1/2. What's 1/8 plus 1/8 plus 1/8 plus 1/8? It's 4/8. That's 1/2. How many 1/16ths are there? There are 8 of them. That's 8/16. This is 1/2. So what's going on here? What's going on here is that the original series, the sum n goes from 1 to infinity of 1 over n, is more than 1 plus 1/2 plus 1/2. That's not geometric that I'm looking at now. 1/2 plus 1/2 plus 1/2 plus 1/2 plus... What does that series do? If you're not sure about it, look at what it equals. 1 plus, what's 1/2 plus 1/2? 1. Plus, what's 1/2 plus 1/2? 1. Plus 1, plus 1, plus 1, etc., etc. I have 1 plus 1 is 2, plus 1 is 3, plus 1 is 4. This series diverges. If you have a series if you have a series in which you just keep adding 1, the series blows up. So the sum 1 over n is greater than a series, is bigger than a series that goes to infinity. So it's dragged up there too. So the sum 1 over n must also approach infinity. Since it's greater than a series that approaches infinity, it must be dragged up there too. That is, the sum 1 over n diverges. This is an extremely important series for us. Diverges. The sum of 1 over n diverges. This series has a special name. This series, which I'm also going to highlight as being a real important series, this series is called the harmonic series. This series is called the harmonic series. Harmonic series. And what do we do with it? We memorize what it does. The harmonic series diverges. Okay, what I'd like to end our section with is one test to determine that a series diverges, one example, and a couple of ending remarks. Okay, now let's take a look at what must happen if a series converges. If a series converges, if a series, the sum, n goes from 1 to infinity of a sub n converges, then what must be happening with the individual terms in the series? What must be happening if we have a convergent series? What must the individual terms approach? If we start eating lots of pizza, let's put it in that term. If we keep eating more and more and more slices of pizza, then what must be happening with the individual pieces of pizza as time goes on? They'd better be shrinking down to nothing. The way we state that in general is that if a series converges, then the individual general term, the sequence of numbers, must approach 0. This is an extremely important theorem. We almost never use the theorem in this form, though. We mostly use the theorem in reverse. Now, I don't mean reverse literally. Okay, so let's back up a little bit. So if a series is known to converge, then the general term, the sequence of numbers, the numbers on the waiter's list must be getting very small. But this is not a test for convergence. It tells us what happens if we know a series converges. If a series converges, then the general term must go to 0. It doesn't say the reverse. This theorem, and I'm going to identify it as a theorem. This is an important theorem. This theorem cannot be read in reverse. Don't read this backwards. The reading of this theorem backwards is a gigantic source of mistakes with students. In more harsh terms, reading this theorem backwards has traditionally been a large source of point loss on a test. Huge source of point loss in a test. This theorem does not say, if a sub n approaches 0, then the series converges. It's not saying this. Does not say this. Not say this. If it's not saying if the pieces of pizza are getting 0, then when you add them up, you get convergence. I'm gonna highlight this. I'm going to highlight this in red. It's that important, and it's that important that we spend more time on this. The sum 1 over n ranges from 1 to infinity, diverges. It's the harmonic series. But a sub n, which is 1 over n, approaches 0. For both the dates on this pizza date, both of them involve, both of their orders involve slices of pizza that were approaching 0. The general terms of their series approach 0, but only one of them converged. So if the general term approaches 0, we know nothing about whether the series converges or diverges. If the general term approaches 0, we know nothing about whether the series converges or diverges. The theorem says that if your series converges, then the general term must approach 0. It does not say the reverse. We can reverse the theorem if we negate the things in the theorem, the items in the statements in the theorem. So this is how we actually use this theorem. The form of the theorem that is useful to us, not to use, but to us, is the reverse of the theorem, the way we can reverse it logically. So the theorem says, if series converges, then general term approaches 0. So if the general term does not approach 0, then the series diverges. This is an important test for us. This test we call the test not for convergence, but it's a test for divergence. It only tests for divergence. And we're going to highlight this theorem as one of the important things for our whole chapter. The test for divergence says that if the general term of the series, that is the things that you're adding together, do not approach zero, if the slices of pizza are not getting small, then when you add up all the slices of pizza, when you consider the series, it will diverge. So, here's the bottom line. If a sub n approaches zero, then we know nothing. What do? Well, if we know nothing, then we try to use another test. And we're going to have, as I mentioned, we're going to have a whole bunch of tests, a few tests, not a whole bunch, some tests coming up in our next sections. If a sub n does not approach zero, then the series diverges. If you can stick to this bottom line, you're going to be safe in a place where your Calculus 2 ancestors, past 30 years I've been teaching Calc 2, haven't been safe. So let's look at an example. Determine whether the series converges or diverges. And the series is the sum n over n plus 1. N goes from 1 to infinity. Well, what does this series look like? When n equals 1, you have 1/2. When n equals 2, you have 2/3. N equals 3, you're adding 3/4. So that's what the series looks like. It's not geometric. It doesn't look like a number plus a number times r plus a number times r squared. Okay. Look at the terms in the series. 1/2, 2/3, 3/4. The general term, a sub n, is n over n plus 1. What are those terms approaching? They're getting very, very, very close to 1. Look at when n equals 5,000. You have 5,000 over 5,001. That's very close to 1. Look at 5 million for n. 5 million over 5,000,001. That's even much more close to 1. The general term, the individual terms in this series are approaching 1, and that's not 0. So the series diverges, and what you write on your homework and on your test is y, by the divergence test, or test for divergence. Divergence test, or as I wrote above, test for divergence. You can use either expression. Okay, so a couple of things to end the section. No more real difficult theory and stuff. If you have a series, let's say 5 over n, that series is not the harmonic series. That series is not the harmonic series. The harmonic series doesn't have 5 over n, it has 1 over n. But you can factor out constants from sums, just like you could do in algebra. You can factor out a greatest common factor, or you can factor out common factors from sums, just like you could using the distributive property, the reverse, I guess, of the distributive property in algebra. So constants can be factored out of series without affecting the convergence or divergence of the series. Okay. There's a couple of other results here that seem logical. They seem like they should work, but we have to be careful with them. If we have, let's say, the sum of a sub n plus b sub n, we can split this series into the sum of two series only if the individual series converge on their own. This is an important thing. We can do this only if the sum of the a sub n as a series and the sum of the b sub n separately and on their own converge. Okay, so we can't distribute sigma inside of addition or subtraction unless we determine that the sum of the a sub n's and the sum of the b sub n's converge on their own. Okay, be very, very careful with that. All right. So the last thing I want to talk about is, it's called the tail end theorem. It's not a real complicated thing. It just sounds complicated. The tail end theorem. And it has to do with where in a series does convergence or divergence occur. Now, what I mean by that is, a series is obtained by adding an infinite number of numbers together. A series never has a finite number of terms in it. A series is always obtained by adding an infinite number of terms. So if I have any finite sum, that is, assume I add any finite number of numbers together. Suppose I add 1 trillion numbers together. Is it possible for that sum to add 1 trillion numbers together and have something that diverges? No. If you add two numbers together, no matter how big those numbers are, that result will be finite. The same thing is true if you add 5 numbers together, or 500 million numbers together, or 1 trillion numbers together. So convergence or divergence doesn't happen in the first part of a series. What do I mean by the first part? The convergence or divergence never occurs by adding the first finite number of terms together, however many those terms might be. A better way to state this would be that convergence or divergence occurs as n approaches infinity. So if you have a series, let's say the sum n goes from 1 to infinity, you can consider that series as the sum of the first any finite number of those terms together. Let's say a sub p, and p could be very large, but it will have a lot more terms. It will have the p plus first term, the p plus second term, and it will keep on to infinity. So the sum, any series, can be broken down into adding together a finite number of terms. And again, that finite number of terms can be a heck of a lot of terms. I'm trying to erase something here. That finite number of terms can be a whole lot of terms, plus an infinite number of other terms. A sub n. In fact, what I'd like to do, if my surface will allow me to, I want to move this second part over. There we are. I got lucky here. Okay. Oops. I got lucky and lost my luck. I'm trying to make it produce. Okay. There it is. Okay. So the sum of any series can be the sum of the first p terms plus the rest. It's in the rest of the terms where convergence or divergence occurs. This rest is called the tail end of a series. The tail end of a series starts at some point forward to infinity. And that is where convergence or divergence happens. The first trillion terms of a series do not affect the convergence of a series. It's the rest of the terms. It's the infinite number of terms after that. So I want to end with a couple of statements. Removal of a finite number of terms from a series. If you remove any number of terms, finite number of terms from a series, removal of a finite number of terms from a series does not affect whether the series will converge or diverge. So the removal of a finite number of terms does not affect convergence or divergence of a series. But if you remove a finite number of terms from a series, see if you can fill in the blanks. You definitely affect the what of the series if the series converges. If you take out a finite number of terms, if you remove 500 million terms from a series, you're not going to affect the convergence or divergence of the series. But if that series converges, what do you affect? What goes in the blank? If you thought of it, great. You do affect the final value of the series. Okay? In the pizza example of convergence, in the series where you had in the geometric series 1/2 to the n minus 1, n goes from 1 to infinity. We had one pizza plus a half a pizza plus a fourth of a pizza plus an eighth of a pizza, etc., 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 and that converged to 2. Removing 1.5 pizzas is not going to affect whether the series converges or diverges. Convergence occurs as n approaches infinity, or divergence, but it certainly is going to affect the value of this convergent series. The series converges to 2. If you remove 1.5, the new series now converges to 1/2. Okay, so we don't affect the convergence or divergence, but we certainly affect the value. Okay, so for that reason, when we're considering series and we're not interested in the value of the series in the case of convergence, we may simply write for series the sum a sub n for the sum n goes from 1 to infinity, or 2 to infinity, or 3 to infinity, if we're only concerned with whether a series converges or diverges. If we're not worried about the value of a series, we can simply write, specifically for the harmonic series, the sum 1 over n. It's always assumed for series that we're going to infinity, so there's no need to write infinity as the upper index of summation. And it's not important if this series starts at 1 or 50 or 5 million or a trillion. If we're only considering whether the series converges or divergence, where we start the series is unimportant. Okay. All right. So that ends this very long section, 11.2, Introduction to Series, and I'm looking forward to talking with you again soon.